Welcome to Mastering Solutions. In this problem, it's really important to stay organized. So let's first make a list of all the information that they give to us. L, or the distance from the diffraction grating to the viewing screen, they tell us is 2.4 meters behind the grating, so 2.4 meters. We are told that the diffraction grating has 500 lines per millimeter, so D is going to be the width over the slits. And so that is, the width is per millimeter, so 1 millimeter is 1 times 10 to the negative 3 meters, divided by 500 lines or slits, same thing. And then we could figure that number out, but I'm just going to plug this in. And they tell us that we're shining visible light, so the spectrum range is 400 nanometers to 700 nanometers. And what we're going to do is we're going to basically say, because they're using this white light here, it has all of the spectrum in it. So they're saying all of the wavelengths are in here. They're just telling us this is the minimum and the maximum of the wavelengths that we're going to use. So before we get into that, let's write down the equations that we'll be using for this. We need to figure out how wide are the spectrums for the different M values. So that's going to be the delta Y. And to find delta Y, we're going to use two equations. The first one is, of course, Y, and that equals L times the tangent of the angle. But we don't know what theta is. And so to find theta, we have to use that equation. And it's given to us as sine of theta is equal to m lambda over d. But it's not solved for the theta, so let's do that by taking the inverse sine of both sides. So we have theta is equal to the inverse sine of m lambda over d. So now these are all the equations we're going to use, and we'll plug this straight in. So I guess we can rewrite it if we want. Y is equal to L tangent of the inverse sine of m lambda over d. All right, so this is the equation that we'll be using for this. Now, how do we accomplish this? What is delta Y, first off? That's how far from the center of the diffraction grating patterns out to whatever M value we have. That is the distance here, and that's what we're going to use. So they want to know how wide is the spectrum? Well, we're using white light, so that's why we're going to use the minimum and the maximum so we can find the furthest and smallest points, and then that'll tell us how wide it is from that. If that was confusing the way I said it, it'll make sense here in a second. So first we need to find the Y for the 400 nanometers, which of course is 10 to the negative 9, and that is a blue color. So I'll put 400. I guess I should have done this in blue. So there we go. Okay, so blue, and we have Y, we'll say Y1 of 400, and that's equal to Y, and that's equal to L, which we said is 2.4 meters, times the tangent of the inverse sine of M, and we're saying M1 because we want to know what corresponds to M1 here. So 1 times the wavelength we said is 400 times 10 to the negative 9 meters. And that will all be divided by D, which we said is 1 times 10 to the negative 3 meters divided by 500 lines. Okay, long equation, but this will tell us how far away is the M1 for the blue wavelength. So let's plug all this in. We have 2.4 times the tangent times the inverse sine of 1 times 400 times 10 to the negative 9 meters. And then that's divided by D, which we said is 1 times 10 to negative 3 divided by 500 lines. All right. So that gives us 0.49, and we are in radian mode. So sorry, that's not degrees, that's the meters. So we have 0.49 2.49 meters. So that's how far away it is from the central maximum out to the first brightest spot. Now let's do the same thing again for M1 for red. So red, and then we have Y1 of 700, and that's going to be same thing, 2.4 meters, tangent of inverse sine. The only thing we're changing here, of course, is the wavelength, which is now going to be 700 meters instead of the 400. Then we have 1 times 10 negative 3 meters divided by 500 slits. Sorry, bad handwriting there. Okay, and then we don't need to rewrite all that in the calculator. We can just take this, steal it, and then let's come over here, and we have 700. So that spot where that central maximum for the other end, because remember, this is white light, which contains all of the wavelengths for visible light. And so that's going to be 0.8 meters. Now we need to do one more, and then we'll come and answer all these. And for this one, we need to do the Y2. So the Y value for the M2 for blue. So let's go back to blue, and we have Y2 of 400 is going to be all the same, 2.4 meters, tangent of inverse sine, only now we have M2 of 400 times 10 to the negative 9 meters. And then 1 times 10 to the negative 3 meters divided by 500. So let's steal this one. And now we want M of 2 instead of M1 and M2. There we go. Okay, so that gives us 1.048. 1.048 meters. All right, so now we can answer the questions up here. So for part A, they say, how wide is the spectrum that corresponds to M1? That's why I said we need to find the maximum and the minimum for M1, which is given basically here, because now we just subtract these two, and that'll tell us how wide that M value is. So we take 0.897 and we subtract meters, 0.49 meters. So you have 0.897 meters minus 0.49 meters. And that gives us the width for the first part is 0.407. You could round that to 0.41 meters. So that's how wide M1, the width of that bright spot is. Now for the second part, how much distance separates the end of M1 from the start of M2? Well, the end of the M1 was the 0.897, and the start of the M2 is going to be the blue again. And so for M2, and so now we just do the same thing. We just take 1.048 meters minus 0.897 meters. So we have 1.048 minus 0.897 meters, and that gives us 0.151. Let's just say 0.15 meters. And that is how far the distance is from the end of the M1 spectrum to the beginning of the M2 spectrum.